Hello, Math 1050. This is Mrs. Bricky, and this video is for section 2.7. We'll be talking about analyzing the graphs of functions. Some of this will get into piecewise functions. We'll talk about increasing, decreasing, mins, and maxes, and we're going to talk about symmetry. To determine if graphs have symmetry, if you have a picture of the graph, you can just look at it. We've got an example of each here. So in the first graph, you can see this sort of parabola-like shape. It's symmetric to the y-axis. And essentially what that means is that whether you look at negative x or x, the function will have the same height. So if I look, for example, at positive 4 and at negative 4, the height of the graph is the same. And that is symmetric to the y-axis. Please note that if this graph, for example, had been shifted a little bit to the right, this is not symmetric with respect to the y-axis. So it still has a vertical symmetry, but it's not the y-axis anymore. Okay, so the next one, symmetric to the origin, is the one that is probably the trickiest for people. Symmetric to the origin is a rotational symmetry. So you can see that, for example, if this function goes through the point 4, 3, if it's symmetric to the origin, it'll also go through negative 4, negative 3. You can think of it like rotating the graph. Let me draw some arrows here. So if we rotate this graph 180 degrees, it lands back on top of itself. So sometimes it's called a rotational symmetry. Okay, and then the next one is symmetric with respect to the x-axis. Now, any graph that is symmetric with respect to the x-axis wouldn't be a function because it wouldn't pass the vertical line test, but it would be a relation of some sort. And you can see that for the same x value, the graph would have both the positive and negative y value. So for the x value 3, for example, this function has a y value of both positive 4 and negative 4, and that's what makes it symmetric with respect to the x-axis. And then that last graph, that petal graph right there, probably a sort of graph that you haven't really seen before, but this sort of graph would have all three types of symmetry. So you can imagine sort of folding it in half, whether vertically or horizontally, and it would be the same graph. And also if we rotated it 180 degrees, it would be exactly the same graph as well. So this one has all three types of symmetry. Okay, so your first topic, you'll just have three graphs presented to you, and you'll just have to decide what type of symmetry the graph has. So this first one definitely is symmetric with respect to the y-axis. And if we think about this line here, it's definitely symmetric with respect to the x-axis. And so then picture if you rotated it 180 degrees, this thing would still be the same. So it is symmetric with respect to the origin. Something that is true is that if it has both x and y-axis symmetry, it does have origin symmetry always. Okay, the next one, you can see that it fails to be x-axis or y-axis symmetric, but if you rotated this thing 180 degrees, it would be the same graph, so it does have origin symmetry. And our last one, we can see that it does not have x-axis symmetry. It's only below the x-axis, so definitely not x-axis symmetry. We do have some y-axis symmetry happening here, and not symmetric with respect to the origin. If we rotated it 180 degrees, it would be an upward-facing parabola, which is much different than it is right now. All right, so that covers deciding on symmetry from a picture of the graph. So the next topic is to decide about symmetry, but this time just from the equation. So I want to look at these little graphs I have on the side and talk about how to deal with the equation. So if you're testing x-axis symmetry, so if you're testing whether it's symmetric about the x-axis, what you're going to do is take the y in the function and replace it with a negative y and see if the equation remains the same. And then to test for y-axis symmetry, you can see this second picture kind of gives an example of that. What we want to do is take the x in the function and replace it with negative x and see if it remains the same. And then for origin symmetry, you need to do both of those. Replace the y with a negative y and replace the x with a negative x and see if the equation remains the same. So that's a little bit confusing, but I think we're going to do several examples of it because it is pretty tricky for people at first. And then hopefully that idea will make sense once you see a couple of examples. Another strategy you could use is to think about what the graph is, but for some of these, you may not know what shape the graph is. So, all right, so we are going to test this equation, 18x squared plus 29y squared is equal to 20. First, let's test x-axis symmetry. So if we're testing x-axis symmetry, we want to replace the y in the equation with a negative y. And because that negative y is being squared, essentially it's the same as if it was a regular y squared. So this equation would remain the same. It would still be an 18x squared plus 29y squared equals 20. So this one does have x-axis symmetry. Let's test y-axis symmetry. And you may not even write any of these things out. You may just be sort of thinking this mentally in your head. So don't feel obligated to write a bunch of stuff out when you're testing these. If you really understand it, it can be sort of a mental check. So to test y-axis symmetry, we're going to change the sign of the x. So this becomes 18 times negative x squared plus 29 times y squared. I don't really need a parenthesis there. Equals 20. And you can see that since the negative x is squared, that is exactly identical to a regular x squared, and so the equation didn't change at all. So this is symmetric with respect to the y-axis. If your equation is symmetric to both the x-axis and to the y-axis, it will be symmetric to the origin. But if I was formally writing that out, it would be that I'm replacing both the x and the y with a negative version of themselves. And you can see since they're both squared, that's the same as if I hadn't made them negative. So this is also symmetric with respect to the origin. So in this case, we have all three types of symmetry. Just FYI for fun, this is an ellipse, kind of like the first graph we looked at. Okay, our next equation is y equals 7 minus x squared. So we're going to start by testing the x-axis symmetry. That means we're changing the y. So this y becomes a negative y, 7 minus x squared. So in this case, this is not the same equation. The right-hand side, 7 minus x squared, remained the same, but the left-hand side changed to a negative y, and there's nothing I can really do to simplify that. So this fails to have x-axis symmetry. So we're going to test the y-axis symmetry by changing the x to a negative x. So this would be y equals 7 minus negative x squared. Well, that negative x squared is the same as a positive x squared. So this is the same equation. And so yes, this thing does have y-axis symmetry. If your function fails to have one of x-axis symmetry, or like if it has one but not the other, it won't have origin symmetry, but you could think about testing it. It can have origin symmetry with neither x or y axis symmetry, but it it can't be a split there. To test the origin, we would replace both. And you can see that the y over here would stay negative. The x could be written this way. And again, this is actually the same equation as the first equation, which is not the same as the original. So that's a no. So this one only has y-axis symmetry. If you're good, you could probably think of the graph to help you do this one. It's a reflected parabola that's been shifted up 7 units. So if I graph it, you can kind of see that it does have that y-axis symmetry, but not the other two. Okay, y is equal to x to the third power. Let's start by testing the x-axis symmetry. So we're going to change that y to a negative y, so our equation becomes this, and that is not the same. Not the same as the original. We're trying to make it or see if it is the same as the original. So no x-axis symmetry here. We're going to test the y-axis for symmetry now. So we're going to replace the x with a negative x. Negative x to the third power is the same as negative x to the third power. When I say that, that's funny. So in this case, this is still not the same as the original function. And so we don't have y-axis symmetry. Let's test origin symmetry. So we need to change both the x and the y. So negative y equals negative x to the third power. Well, this is the same as this. And if I divide by negative 1, I have this. And again, what I did was I sort of thought about dividing both sides of that equation by negative 1. So this equation that I now have is the same as my original equation. So this does have origin symmetry. So it can have origin symmetry on its own, or it can have origin symmetry if it has both x and y-axis symmetry. All right, this graph, just in case you're kind of picturing it, it does look like this. So it does have that rotational origin symmetry. Okay, this last one, let's test it for x-axis symmetry. So we're going to replace that y with a negative y. This is just not the same as our original. If I maybe tried dividing by a negative 1, I would end up with this. This is not the same as the original. So this does not have x-axis symmetry. If we test for y-axis symmetry, we would replace the x with a negative x. So this would be y equals 5 times negative x minus 7. That's negative 5x minus 7. That is definitely not the same as my original. And if we test origin symmetry, we're going to replace both the y with a negative y and the x with a negative x. And in case you were thinking this was going to work, look at this. So we have negative y on the left. On the right, we have negative 5x minus 7. If we divide that whole equation by a negative 1, we have 5x plus 7. It's so close to the original, but the 7 has the wrong sign. So this is also a no. No, I almost marked it yes. This is no, no, no. This particular equation has no symmetry to it. It is a line. Hopefully you recognize that as a line. It's a line with a y-intercept of negative 7 and a slope of 5. So it looks something like, this is a kind of rough sketch here. Let's see. I'm going to actually use the line tool because I can't get it straight, but it's a very steep line that has an intercept of negative 7, so it's not symmetric in any way. Okay. Last one. I picked this one because it gave some people trouble one semester. So we're going to first test x-axis symmetry by changing the sign of the y. So this becomes a negative y squared minus x plus 5 equals 0. but this is the same as y minus x plus 5 equals 0. So that is the same. So we do have x-axis symmetry here. Testing the y-axis symmetry by changing the sign of the x, we have y squared minus negative x plus 5 equals 0. This is y squared plus x plus 5 equals 0. That is not the same. So no y-axis symmetry. And then finally for origin, we change both signs. So we get y squared plus x plus 5 equals 0. Again, that is not the same as our original. So this one only has x-axis symmetry. All right, that's it. I know we did a lot of those. The rest of our topics I don't think are too bad. That symmetry one seems to be the hardest one for people. All right, so the next topic has to do with where functions are increasing, decreasing, or constant. So a function is increasing if you see it rising from left to right. It's decreasing if it's falling from left to right. And constant means that it's staying at the same height. When we talk about intervals of increase, decrease, or constant behavior, we are always reporting our answer in interval notation. And those intervals are essentially portions of the domain. We are breaking up the domain into pieces of increase and decrease. So we are always using x values. Always, always, always for this particular topic. For intervals of increase and decrease, always x values. We're not thinking about how high the graph is. We're thinking, where does it increase? Where does it decrease? And so that means we're talking about x values. So I'm going to go ahead and highlight my x-axis here to remind me of that. This question says, determine the interval on which the function is strictly decreasing. Write your answer as an interval or list of intervals. When writing a list of intervals, make sure to separate each interval with a comma and to use as few intervals as possible. So that's what your instructions are going to say in ALEKS. So if we think about where is this function decreasing, this function is decreasing. Remember, we always think left to right. So I'm going to kind of read through this function. First, it's constant, then it's decreasing, then it's constant, then we've got a little increase, and then finally we finish with a decrease. So we have two intervals on which the function is decreasing. And I'm going to highlight those in blue on that x-axis. So we would have to list our answer as two intervals. It's from -4 to -2. That's our first interval. And we'll put a comma. And for our second interval, we'll say from 2 to 6. And again, those are x values. So I'm not thinking about that it's a height of 3 here. I'm thinking about that it's between the positive 2 and the 6. You may have in the past used a union symbol here, but don't use a union symbol for this topic specifically. It is telling you to separate the intervals with a comma, and you do need to do that. It will mark it wrong if you use the union symbol here. Also, please note when it says to use as few intervals as possible, it just means that it doesn't want you to do something like this, from -4 to -3, from -3 to -2, where I've sort of broken up this interval into two pieces. That's what it means when it says in as few intervals as possible. So our answer with two intervals would look like this. Okay, next topic is finding local maxima and minima of a function given the graph. So anytime it's saying local, it also could be the word relative. Those two words mean the same thing. So a local max is also called a relative max. A relative max or a local max is a high point on the graph. So it doesn't have to be the highest, it just has to be a high point compared to the values around it. So you can see that this is a high point compared to the values around it. And, in this case, it's high compared to a pretty big interval, but it can be a very small interval as well. It just has to be a high point. Relative min or local min would be a low point on the graph. In this topic, it's going to ask you two questions. It's going to ask you the values at which G has a local min, and it's going to ask you a question about what are all those local min values. It won't always ask them in this order, so I have the values at which first, and I have the local min values second, but it does shuffle the order here. And so you really have to read it and pay attention, and you have to know which one is which. It doesn't say this on the screen. I put this here. So when it says the values at which G has a local min, that is asking you for that X value. It's asking you where they occur. When it says all local min values, that's talking about values of the function. So that's asking you for Y values. This topic often comes up on tests, and honestly, people miss it all the time. And it's because of two things. They either mix up the X and the Y, or they don't notice or don't register that it's asking for a min or a max. So they'll list either all the mins and maxes, or they'll list the maxes when it asks for mins, or vice versa. So this definitely is a question where you have to read what it is asking you, and you need to pause and process what it is asking you, and not just hurry and type it in, because conceptually it's pretty easy to find a min or a max, but if you're going fast and not processing the words, you can put in the wrong numbers, even though you totally understand it. So for this one, we're looking for mins. So we're looking for low points. On this graph, I have two mins. Please note, on my graph, they have the same height, but if they would still both count as mins if this one dipped down a little bit lower. So the mins may have the same height, they may have different heights. They just have to be a low point on the graph. So we are looking for mins. The values at which G has a local min are -4 and 0. For the second part, it is asking you what those local minimum values are. And that is the one that is asking you for the Y values, local min values. In this case, we only have one thing to list, which is -1. If this one had dipped down lower like this, we would list -1 and -2. So if you have more than one, you'll separate it with a comma. Okay, the last two topics, it's actually three topics in ALEKS, but the last three topics have to do with piecewise functions. So piecewise functions are functions that do different things on different parts of the domain of the function. So they have these vertical, pieces. You'll see a brace always, and then you'll have more than one equation listed. So on this one, I have 1/4 x minus 2, and I also have the equation 4. And then next to each equation, it will tell you for which x values that applies. So this first topic is just evaluating a piecewise function. So we have our function here, h of x. Our first question says, what is h of -5? Well, -5 is an x value. So what you have to do is decide which piece does that x value fall in. So our first piece is x is not equal to -1, and the second piece is for x equals -1. Well, our x value, -5, is definitely not equal to -1, so we will use this piece. So our answer is 1/4 times -5 minus 2. And you'll want to use your calculator. I mean, you can do it in your head, I guess, if you want. Definitely this is a fraction answer. And you do want to leave it in fraction form. And so that answer is negative 13/4, and you can use your calculator to get that. Our second is h of -1. Well, -1 is equal to -1, so this would be our solution 4. And there's nothing I need to do there. It's just if x is equal to -1, the h value or the y value is 4. So 4 is my answer. Our last one is h of 2. So we're thinking about the x value 2. Well, 2 is not equal to -1, so we'll use this piece. So this will be 1/4 of 2 minus 2. And you can use your calculator to evaluate that or do it in your head. And this would be -3/2. So you use the x value to decide which piece to use. A second one, just because in this one, all of the pieces are constant. So I just have to decide which interval it goes into, and then I can get my output. So f of +1, well, +1 is equal to 1, so my function's value is 1. F of 0.75, well, 0.75 is in this interval. 0.75 is definitely between 1 and -1, so my answer, between 0 and 1, so my answer would again be 1. And then the last one, f of 2, well, that's in this group right here, so the answer here would be 2. Okay, the last two topics are graphing piecewise functions. Some of these are a bit of a pain. I've seen them with 5 pieces before. Usually if they have 5 pieces, they're all constant. So there are 2 topics of graphing piecewise functions. The first one will just have you graph it. The second one has this follow-up question of, is the function continuous? Continuous means like fully connected. So it wouldn't have any no jumps where like the function has a break in it. So we're going to do 2 graphs here. So if first piece is -5, if the piece of the function is a constant value like this is a horizontal line, or a little horizontal piece of a line, I guess. So the line -5 is this line. I'm dotting it because it's piecewise function, so we only have that for a specific domain, and that is only if x is less than -2. So my x's that are less than -2 are over here. So I just have this sort of left side of that horizontal line. I'm going to erase the rest of the dots. Our middle piece is the equation x minus 3. So this is a line. It's a line with a y-intercept of -3 and a slope of 1. So my y-intercept is -3, and I'm going up 1 over 1. So it's going to be this. And the domain of that particular part of the function is between -2 and +2. So it starts here at -2, and that is an included value. So it's kind of like filling in that hole. And it goes over to +2, but that one's an open circle, and it's just all the x values that are in between there. So again, I'm going to erase off this right-hand side. Those 2 pieces connected, so like if this was my graph, I would say it's continuous. But let's see what our last piece does. So our last piece is a constant again. So this is horizontal. It's horizontal at a height of 1. So it would be this. The domain of this piece is for x values that are greater than 2. So we would have a filled in circle here because it's including that x value of 2, and it's all of the x values that are larger than 2. So I'll erase this time everything that is to the left of that particular x value. So this one, because of this last piece, this would be not continuous. And again, the reason that it's not continuous is because of this jump right here. Okay, let's do one more graph. Some of your graphs may have parabolas in them. In ALEKS, these are kind of challenging. Sometimes you have to cut the shapes to remove pieces. If you need help with that, let me know and I can help you. So this first piece is a parabola. It's a parabola that opens downward and it got shifted up 10 units. So our vertex would be right here, and you'll have a tool to graph the parabola, but it will draw the whole parabola. It'll just draw everything. Oh, this is not pretty. You only want to keep a portion of that. The domain for this piece of this parabola is between -3 and +3. So what you'll do is you'll need to tell ALEKS a point that you want to cut that graph at. So we would want to cut the graph at -3, 0, and you'll have to sort of decide what the height is because you need both the x value and the y value to cut it. So if you typed in these 2 points into the cutting tool, ALEKS would put a cut here and here. It shows up on ALEKS as a little X. And once you do that, you can click on different pieces and delete them. So we could delete these 2 pieces. Now on the left-hand side, you would want to put in a filled in dot, and on the right-hand side, we would want to put an open circle. So that's the first piece of our graph. The second piece, oh, you know what? Sorry. My sketch of my graph is so bad that I have these at the wrong height. They would actually be 1 unit up right here. If you're having a hard time telling exactly the, oh, and I flip-flopped that. If you're having a hard time telling the exact y value, what you want to do is just sub those x values in. So this y value should be 1. And you can get that by saying -3 squared plus 10. So just subbing it into the equation, that equals 1. And then -3 squared plus 10 also gives you 1. So you can get those y values from the function if you're having a hard time on your grid telling their height, like I was having a hard time telling on my grid because my sketch was poor. All right, so we've got that first piece settled in. So the second piece has the equation 1 minus x. Well, that's a line, and you'll maybe recognize it better as a line if we write it in standard form. So this line has a y-intercept of 1 and a slope of -1. So the y-intercept of 1 is here, and the slope is that it's going down by 1 step. So we obviously don't want to keep the whole line. We just want to keep a portion of the line. This is for all x values that are greater than 3. So we've got greater than or equal to 3. So we've got a filled in circle here, and then the line continues down. So again, in ALEKS, you might be able to just do a ray for a line, but if not, you would want to just make a cut right there and delete the other half of the line. So we've got our graph now. The follow-up question is the function continuous? You would just want to look for if it connects or not. So for this example, it would be no. If this section of the line had been like right here, then we would say yes, it is continuous. But since ours is down here, that's a no for continuity. Okay, that's the last topic of this section. So let me know if you have any questions. Test number 1 is coming up very soon, so we'll be reviewing and getting ready for test 1 next. So let me know if you have any questions about this section. Thank you.